In this video, we're going to discuss the concepts behind our design procedure in bending, shear, deflection, and then bearing. Okay, so for bending, this is an extension of the discussion from lateral stability. And so the first quantity that we need to define is our slenderness ratio, RB, which is the measure of tendency of a member to buckle laterally due to insufficient lateral support. What that means is that if our member is slender or has a high slenderness ratio, the beam has a large susceptibility to buckling. Like for a ruler, it's a very slender element, right? And if it is slender, it is more susceptible to buckling. However, if you can think of a member that is not that slender, and that means maybe it's just short, or maybe the section is bigger, and therefore it has a low slenderness ratio, what would happen? The susceptibility, the tendency to buckle is also low. And so if the slenderness ratio is high, the tendency to buckle is also high, and the strength of the member is low. But if the slenderness ratio is low, then the tendency to buckle is also low, but the strength is high. Okay? And we can see that RB here is a function of the effective unbraced length, LE, and also the geometry of the section. The higher the effective unbraced length, the higher the slenderness ratio. As we can imagine here, compared to its geometry, its length is large, and therefore this is slender, and the slenderness ratio is big. Okay? But we have not yet defined what LE is. What is effective unbraced length? In the previous video, we just discussed unbraced length. So, how do we define that? There is a table here for different loading configurations, for cantilever beam, and then for single span beam. But for 133, we will just use this one, so that calculations would be simpler. Okay? So either it is cantilever or single span beam, then we will use this conservatively. Okay? Now, it depends on the value of LU over D, unbraced length over the depth of the section, and depending on that, we have our effective unbraced length. And we will use that for our RB here. Now, RB, or the slenderness ratio, has an acceptable range of 0 to 50. It means that if you have a slenderness ratio of 50, that's very high already, and it's not advisable to design a beam with such a slenderness ratio. Why would be that? Why would be the case? If our member is so slender as to the slenderness ratio reaching 50, that would mean that maybe we're not being efficient in the use of our beam. And so it is good to limit the slenderness ratio to this range. Okay? And then next, if we have RB, we can use that to get FBE, which is the Euler-based critical buckling value for bending members. What that means is that this is the value, or this is the stress in which buckling occurs. Okay? It's the limiting stresses, which is a function of E prime mean, the adjusted design value for E mean, over RB squared. Okay? And if we have FBE, we can solve for CL. But also, we also need to find for FB star. And what is FB star? So we have here FB times product of applicable adjustment factors except CFU and CL. Remember the different adjustment factors applicable for FB, so we will use that, except for CFU and CL, and then multiply that with FB, and then we have the FB star. And so if we have FBE and FB star, we can compute for CL, which would be the beam stability factor, the only adjustment factor that is lacking for FB, if you will remember from our previous discussion. As I have said, as the slenderness increases, the bending strength decreases, as we can see from this figure here. So a graph of the adjusted bending design value FB star versus the beam slenderness ratio. And as we have said in the previous slides, the ratio should be limited to 0 to 50. If it is 0, then we have a very high FB star, or the adjusted bending design value, and then it lowers up to RB equals 50. Okay? And so the higher the slenderness ratio, the lower CL is, and consequently the lower the adjusted bending design value. And then in case we have a laterally supported beam at the whole span, then we have CL equals 1. I think I've mentioned it in the previous video, but what would that look like? Okay, we have here a girder, and as you can see, it is connected to a diaphragm, or simply a floor. And the floor, it should be a structural member. The floor would act as a lateral support for the whole beam. And in that case, LU would be 0, and consequently, CL equals 1. And so, mas maganda kung palalangin nyo na laging fully laterally supported yung beam natin so that CL is only equal to 1 and you don't have to compute for it. And that's all for bending. So we can now compute for FB prime, including CL, and then we will just compare that with this bending stress. So next, for shear, so we already know how to compute for the strength, FV prime, and computing for the stress, which we addressed in the first exam. But we have to note here the critical shear force. So normally, in the previous subjects, when we compute for the shear force, or the maximum shear force, let's say we have a uniformly distributed load, we will expect that the shear diagram would be this one, triangular in shape. However, in reality, the support provides some kind of rigidity around this area here, and also, of course, at the other end. And so we can say that the critical shear force would be at a distance d from the face of support. Okay? Let's say we're designing a beam, and then you've computed for the stress at the ends, and you've noticed that the beam cannot carry that kind of shear force. What this means is that we can compute for the shear force and consequently shear stress at the d distance from the face of support, and if that qualifies, let's say that the stress here at this point is lower than our adjusted strength, and so our beam is what? Our beam passed. Okay? So even if it fails at the ends, if it passes to, if it is adequate at a d distance from the face of support, then our beam is still considered adequate. But there's a caveat, as I have highlighted here. Provided that no concentrated load occurs at this region. As you can see here, this is just a uniformly distributed load. But let's say we have a moving load here, then that would not apply. Okay? So next, for deflection. Okay, deflection is a subject, or was taught from NSI 13, as I would expect, but it is further discussed in C132, which is not a prerequisite of C133. So let me just say that I would assume that you don't know how to get deflection, and maybe you have forgotten. So in that case, I would just give the formulas. So let's say we have a simple beam, simply supported beam, and then subjected to uniformly distributed load. The maximum deflection would be 5WL to the 4 over 384 E prime. Okay, E prime I. And then for point load, we have PL cube over 48 E prime I. E prime stands for the adjusted modulus of elasticity. Not the minimum, not E min, but E. Okay? And I would also advise that you memorize these formulas, although, open notes naman ang exams and exers natin, but these formulas are so important up to board exam, and maybe even when you work as a structural engineer, if ever you would choose that. Okay, so this is how we get the maximum deflection, but how can we know that our beam is adequate, or how can we know the allowable values, we will use this table here, right? So we will solve for the live load deflection and also for the total load. For the live load deflection, the deflection limit is L over 360. That means the load should only be live load. Even if a dead load is given, we will only compare L over 360 with the live load. Okay? But for the total load, we will compare it with L over 240. Now, please read this footnote here for the computation of the total load, which is a function of dead load and live load. Okay? Next, for bearing, just a simple formula for getting the stress. We have the reaction over the area of bearing. Okay, and what would the area of bearing be? So we have, let's say we have this configuration here, and then as you can notice, this part here would be the area of bearing. And so it's just the thickness B times the length of bearing. Okay, so B at this part here and the length of bearing. That would be the area, the bearing area, and then we can get the stress. Or if we are looking for the bearing length, and we just have to transpose the quantity, so R over B times FC prime perpendicular. Now it depends on the configuration or the connection. There can be different bearing length configurations, as you can notice here. So if in the case of this connecting beams but there is a clearance, then the length of bearing would be the overlap, or not the overlap, but this part here. And then next, if we use a gusset plate, then that would be this point to this point. Next, if there's an overlap, that means there's a beam that goes here and then another that goes here. The overlap, the available bearing length would be the beam, the supporting beam length or thickness. Okay, and the next for joist hanger would be this part here. Okay, so you should be aware what is the connection configuration for you to determine the bearing length and consequently maybe the bearing stress, or depending on the type of problem. So you may know if it is adequate in bearing.